Welcome back. We continue with black box testing. One important way of introducing black box testing is to call it as functional testing, because we're going to focus on testing functional requirements. We saw what a functional requirement is last time. And there are high-level techniques that have been practiced for several decades in the category of functional testing. We will deep dive into one or two of these techniques, but the purpose of this lecture is to give you the most popular techniques of functional testing, tell you what functional testing is, and explain some of the popular techniques. So just a recap, we've so far done white box testing, white box test case design algorithms. We looked at graphs, coverage criteria over graphs. We applied it to code. We applied it to sequencing constraints. We also applied it to finite state machines, which were requirements, but we still had an idea of a lot of structure. Then we looked at logic coverage criteria. We again applied it to decision statements that come in code, preconditions that come in sequencing constraints, guards that come in finite state machines. Then we looked at symbolic testing. A lot of them looked at code, at various aspects of design, actively knew several parts of the code, its structure, and the test case design techniques were based on that. Now, as I told you in the last lecture, we'll step back and not look at the structure of code or design artifacts. We're going to do black box testing. It treats the code or the design document as a black box. It doesn't worry about the internal structure. What are the statements? What is the design? But it's available as an executable entity for you to execute your test cases. Black box testing techniques deal with inputs, outputs, and the requirements. And the requirements could span the entire software, individual methods, a set of methods, a particular functionality, anything that is available to us. The term functional testing was introduced by Howden, who is credited to this term, in the late 1970s. Mathematically, we all know what a function is. Function takes a function f from x to y, maps elements in x to elements in y uniquely. The idea in functional testing is to test for functional requirements by viewing the program as a function that takes inputs and transforms these inputs by producing outputs. So a program takes inputs, let's say xi, runs, executes, and the outputs that it produces, let's call them yi. So the program can be thought of as a function that maps the inputs xi to yi. So yi is nothing but p executed on xi. Yi is p of xi. For example, suppose I write a program to sort an array of numbers, quick sort or bubble sort. So the sorting program can be thought of as a function that transforms an input xi of unsorted array of numbers and produces an output which is the array in the sorted order. Similarly, let's say I have a program, Java program, and I pass it through a compiler to make it executable. A compiler can be thought of as a program that takes as input the user-written application code in Java or appropriate programming language, and the output is the compiled code, compiled object code. So this can be thought of as a function that transforms one program to another program. So the core idea in functional testing is to view a program as a function that takes inputs and transforms the inputs into outputs that it produces when the program runs on these inputs. Important steps in functional testing are, we should know what our inputs are. We should know that the program has inputs of certain data types, what we call the domain of the input. It has some integer inputs, it has some string inputs, it has some Boolean inputs, its inputs are XML files, and so on. We should also know what our outputs of a program are. We should know precisely each output, its type, so that we know the domain of the input and the domain of the output. By domain, what I mean is the set from which the inputs come. Like if the inputs are integers, then the domain is the set of integers. If the input is of string type, then the domain is the set of all strings. If the input is an array, then the domain is an array of integers, and so on. Now what we do is, typically inputs could be large. Like for example, if the inputs are a set of integers, then we possibly don't test it on each and every single input. So we select possible values from the domain to test the program on. So the choice of selection is what matters to us. We should select such that the properties that we would like to be tested are all tested. So let's call them as important properties. We also consider combinations of values from input domain. Just to give you an example, I took the example of this railway ticket booking system in the last lecture, right? So while taking one particular combination, let's say the passenger is a male senior citizen, then the concession in the ticket is of a certain percentage, let's say 30% concession. But if the passenger is a female senior citizen, then the concession that is to be given is 50%. So here I take the gender and the age, two input parameters, to produce different outputs in each case. So the combinations of inputs also matter for us to design test cases. We should consider input values such that we also include special values from the domains of the output variables. So as we look at more examples, this will become clear to you all. One important thing in functional testing is, let's say you have a structure like this diagram, what is shown in this diagram. P is the entire program. And let's say for now, your goal is to test this particular function or method that is present within P. This function is not reachable straight out from P, our good old reachability property of the RIPR criteria. But this function is reachable only if the input to the program P, let's say X, takes value such that X is greater than 20, greater than or equal to 20. There is some decision that is happening in the code of the program P such that the function f is invoked only if that decision passes. Then that decision, let's say as an example, is x greater than or equal to 20. Please remember, we are doing black box testing. So we may not get the knowledge about this decision being there to reach f and to test f. So sometimes even when we are doing black box functional testing, whenever needed in contexts like these, like for example, I have to test f, and to reach f, I need value of x to be 20. So we say, I take this as a contextual information minimally so that I know how to reach f and I can design test cases that are useful for f. So suppose x was a floating point variable in this case. If I had tested for all possible values of x, but my goal was actually to test the function f specifically, then I would have missed testing function f exhaustively. Let's say x was a floating point number and we weren't aware of the fact that function f that we wanted to test is reachable only when x is greater than or equal to 20. We know that x is a floating point number. We are doing black box testing. So we will design test cases. Let's say we'll take a large number k and then we'll say x is assigned plus k, x is assigned minus k, and x is assigned 0. A positive number, negative number, and 0, and maybe test the program P. Our goal was actually to test f, and f was reachable only when x is greater than 20. So if we were aware of this minimal contextual information, instead of designing test cases blindly like this, x is plus k, minus k, and 0 for some value of k, and invoking the function only once, we would have assigned x to be k, where k is a number, 20 would have been a threshold. So what I'm saying is we would have assigned test cases like this, x equal to k, where k is some number larger than 20, and around the boundary of 20, x is equal to y, where y varies between 20 and this number k that we picked earlier, and we would have tested at 20 also. Because this function was reachable only for values greater than or equal to 20. So if I had to test this function specifically, it would not have been useful for me to give values of x less than 20, negative, 0, or any value of x less than 20. So sometimes in functional testing, which is black box, we take contextual information like this, which involves knowing this, just this part of the code or the design, which will help us to design better test cases, like you see in the last item here below. And this is still black box. We just consider the contextual information as we need it. So there are several different types of functional testing, and these are all the most popular types. The more you can look for them, they are available in several standard testing textbooks, online resources, and so on. The first type that we will see is equivalence class partitioning. Second one is boundary value analysis, BVA. Then we look at decision tables, which is very important because you're all doing a degree in programming and data science, so you will use a lot of decision tables. We'll also look at a very useful, well-practiced functional testing technique, which is random testing. There are testing techniques like orthogonal arrays, cause-effect diagram, which is similar to decision tables. For lack of time, I will not be able to do pairwise testing, orthogonal arrays, and cause-effect diagram. We will do the first 4, and specifically the first one, we will do it much in detail in the remaining lectures of this course because it's the most important black box testing technique. So what is equivalence class partitioning? So maybe I'll start with an example and then I'll come back to the explanation. Please remember, we are doing a black box testing. So we'll always get to look at requirements, inputs, and outputs. We will not get to look at code for a change. So let's say we have the following requirements for a particular software system. The software system is supposed to compute income tax based on the adjusted gross income, AGI. And there are some rules to compute the amount of income tax the person has to pay. These are the rules. So if the annual adjusted gross income is between $1 and $29,500, just as an example, the tax to be paid is 22% of the AGI. If the AGI is between 29,501 and let's say 58,500, tax to be paid is 27% of the AGI. If it is between 58,501, just above this 58,500, and let's say some large number, 100 billion, tax to be paid is 30% of AGI. So we have developed a software that will compute tax as per these rules, and we want to test the software. And these are the requirements that the software should cater to. I want to design test cases for this software. What would be useful kind of test cases? What are the inputs to this? You should first understand. Input is the adjusted gross income. What is the output? Output is the percentage of tax that is to be paid by the user of this income tax computation system. So for designing test cases, I have the requirements, I have the inputs, I have the expected outputs. So my goal is to design test cases. If you look at the style in which these requirements are written, it is reasonably clear to you that it'll be good to test the system by giving it an AGI that falls in this first slab, tax slab, between $1 and $29,500. And by giving it another set of inputs that fall in the second tax slab, $29,501 to $58,500. And again, by giving it a set of inputs that follow in the third tax slab, which is a generous slab. And see whether the program computes the percentage of tax to be paid correctly, right? And you see they are mutually exclusive. If I give an input between in the first slab, it's not going to come into the second slab. And similarly, if I give an input test case in the second slab of AGI, it's not going to come in the third slab, and so on. So what I mean is I take the inputs, set of all inputs. Income could be as low as $1 or income could be as high as 100 billion. Whatever it is, the tax should be computed as per this rule. So that's the set of inputs, income. Output is the percentage of tax. The very nature of this requirement tells you that I can partition or split the inputs into 3 or more categories and test it for one test case per category. That's what we call it as equivalence class partitioning. So as it is, the input domain is too large. I don't want to give one element at a time from across the entire input space and then test the system. So I partition the input domain into a finite number of subdomains for selecting the test inputs. And the requirements are naturally amenable to such a partition, like we saw here in this example. So each such partition or subdomain is called as an equivalence class because as far as the behavior or the output of the software is concerned, it's invariant to any choice of input from within that partition. Is this clear? So the subdomain serves as a source for selecting one test input. Any one input from each such partition or domain is good enough, as we saw for that example. Why is it good enough? Because any input from each partition will result in the software producing the same output. So I might as well test it for one input from each partition. Of course, we will do this equivalence class partitioning or input space partitioning in detail in the next 3 lectures, but this is just to get you started. If you look at these requirements and these inputs and outputs, it will be reasonably clear to you that all the properties that we need for equivalence class partitioning are satisfied. So I would design test cases like this. So there is one more point to be remembered. So if you see here, the first slab varies from 1 to 29,500. Second slab varies from 29,501 to 58,500. So what will happen if somebody earns $29,500, $500.6? Ideally, it should get rounded up to the next slab, but we should test it for this. But what happens if somebody earns more than 100 billion? We should test it for that. What happens if somebody earns less than $1? Not possible, but we should still test the software for that. So I keep all these things in mind and come up with my test inputs, one for each equivalence class. So we get 5 partitions of the inputs. One for the first slab, adjusted gross income is between 1 and 29,500. One is adjusted gross income is less than 1. The next is adjusted gross income follows in the second slab. Fourth one is adjusted gross income follows the third slab. And then adjusted gross income goes, this should be 100 billion, goes more than 100 billion. So 2 of them are invalid inputs. The software should still be able to handle it. And 3 of them are one sample values from the valid outputs. So 5 test cases are enough to test this entire software for its complete set of behavior. Is this clear? So similar to equivalence class partitioning, we have something called boundary value analysis, BVA. It's all about selecting test inputs at the boundary. Like for example, as I told you here, what if somebody's income was less than 0.5? What if somebody's income was $58,500.5 US? Does the software work correctly at the boundaries of these slabs? So boundary value analysis is about selecting test inputs near the boundary of a data domain so that data both inside and outside the equivalence classes are selected. What we call as invalid inputs here constitute boundary values. Boundary values produce test inputs near the boundaries to find values caused by incorrect implementation. Maybe the software worked fine for good values, but maybe it doesn't work fine for outside the boundaries. What happens? Once equivalence class partitioning partitions the inputs, boundary values are chosen at and around the boundaries of the partitions to generate test inputs. Exactly like what we did here. Programmers typically make mistakes in handling at the boundary value, so this kind of testing helps. So typical guidelines for boundary value analysis are partition always specifies a range, as we saw here. There's 29,500, second range, third range. So test around the boundaries. Construct test cases by considering boundary points of the range, points just beyond the boundaries. Partition also specifies number of values. Like for example, if it says tested for a certain number of values that go across an enumerated type. So you test it for minimum, maximum, some value that is not in the value, and so on. Suppose the partition specifies an ordered set, then you test it for the first element, last element, and somewhere in the middle. That's also a useful guideline for BVA. For the example of the income tax computation, we identified 5 partitions for equivalence class partitioning. When I refine that using boundary value analysis, test cases will look like this. For the first partition, that is adjusted gross income between 1 and 29,500, boundary value analysis test cases could be 0, 1, -1. This is practically not possible, but the software should still handle by giving an exception appropriately. 1.5, 29,499.5, 29,500 exact. And as I told earlier, 29,500.5. What will happen in this case? Similarly, for less than 1, you could come up with boundary values. For the second slab, you can come up with boundary values. Third slab, you can come up with boundary values. And for the fourth slab, which is invalid, again, you can come up with boundary values. Software should be able to handle all these properly. Whenever it's not realistic, it should have exception handling procedures. So equivalence class partitioning and boundary value analysis clubbed together constitute very powerful class of black box design test cases where the requirements are amenable to being naturally partitioned into groups that we call as equivalence classes, and one test case per group is enough to test for a particular sub-requirement of the software. These two techniques are very important, so we will devote a few lectures in this week to understand them and how we design test cases across partitioning in detail. I'll move on now and look at briefly the next test case design technique, which is decision tables. Equivalence class partitioning and BVA that we saw considers each input separately. We cannot consider combinations of inputs. So what will happen if we look at combinations of inputs? Decision tables are very useful to test like that. So let me again look at an example and then we will see what a decision table is. Let's say somebody is taking a loan. Let's say a loan for building a house or loan for purchasing a car or whatever it is. In that loan, the software that handles this loan management should have certain inputs. Like for example, they should specify the EMIs, how much to repay per month, what is the total duration. If the repayment procedure is over 10 years, then you pay so much per month. If I'm going to pay it back in 5 years, then you pay a little more per month, and so on. So one condition could be that the repayment amount and the duration has been mentioned. The next one could be the terms of loan has been mentioned. Interest rate is fixed at a certain percentage. Interest rate is floating based on the market demands, and so on and so forth. So there could be a set of conditions which talk about what conditions can be imposed on the inputs, and each of those conditions influence some other condition and they result in some effects. So here, for example, there are two conditions. Repayment amount has been mentioned, term of loan has been mentioned for some software that processes loans of a bank. So Y stands for yes, N stands for no. And there are some steps which allow you for certain combinations of conditions. So in the first step, both the repayment amount and the term of the loan has been mentioned. So they are both marked Y. And the result or the output of the software is that it can process the loan amount. It can start processing the term of the payment of the loan. There are no error messages to be given out. In the second case, repayment amount has been mentioned. Yes, against this condition. Term of loan has not been mentioned. So it's N for no against this condition. Effects are You can process loan amount, yes, but you cannot process the term because that has not been given. And you don't come up with an error message. In the last case, both the repayment amount and the term of loan are marked as no. They've not been mentioned, in which case the effects are, I cannot process loan, amount or term, but I come up with an error message asking for this. So decision tables involve combinations of conditions. It could be one or more combinations of these conditions. And for each combination, what are the effects in terms of the outputs that the software produces? That's what a decision table has. So in general, a decision table will look like this. So it has a set of conditions, let's say some n number of them. Here for simplicity, I have given 3 of them. And conditions can take value y, n and dash, y for yes, n for no, and dash for don't care, or that particular condition, it is not important for a particular decision. Then there are rules or combinations. There can be any number of them as per this set of conditions that are there. Here there are 8 rules. The decision table in terms of the rules for yes, no, don't care combinations need not be complete. It need not have a rule for every possible value of a condition. It's as much as we want it to be. And then there are effects. Effects for each of those combinations. For example, if condition 1, condition 2 and condition 3 are all an S, which is this column corresponding to R1, then the effects will say what to do. E1 will say what to do, E2 will say what to do, E3 will say what to do in terms of the outputs. Effects are do E1 first, followed by E3. That's why this number 1 and 2 is here. So if you take the third column here corresponding to R3, it says condition 1 is met, condition 2 is not met, condition 3 is met. Then the effects are do E2 first, followed by E1 second, followed by E3 third. In the case of R7, where conditions 1 and 2 are both marked N for no, they are not met, condition 3 is met, the only effect is do E2. So this is how you read the decision table. So a table has a set of conditions and a set of effects arranged in columns. Each column corresponds to a combination of conditions and the order in which the effects have to be executed. Each condition has possible value yes, no, or don't care. For each combination of the 3 conditions, or in general any number of conditions, there are a set of rules. They can again be any in number. Each rule has a yes, no, don't care response and an associated set of events. In this case, 3 events in our example. There is a number associated to each event, as we saw here, 1, 2 and 3, which specifies the order in which the sequence of events have to be executed. Effect sequence number specifies the order in which the effect should be carried out if the associated set of conditions are satisfied. So we read enough of that table. So as per that table, if C1 and C2 are true, but C3 is not true, E2 should be followed by E3. Is this clear? So this is what a decision table looks like. These are very useful when you have a lot of data and several combinations of data that you would want to test for. The last kind of functional black box testing, which I would like you to briefly understand, is random testing. As the word says, in random testing, you'd have no specific ways to select inputs. You select test inputs randomly from the input domain. You might wonder, what is the use of such a thing? It's still useful. For example, suppose you had a function that was supposed to compute square root of a number x. Let's say x is a number that can take values from 1 to 10 power 8 with equal likelihood. And you want the square root function to give you a result which will be a decimal number with decimal places, but its accuracy must be within 2 into 10 power minus 4. How will you test this program? Random testing is very useful for this. You can generate uniformly distributed pseudo-random inputs and obtain outputs. For each such generated random input, let's say t, we compare the output z and z squared and then compare z squared with t. Z is supposed to be square root of t. So z squared, you can compare it with t. So if the difference between z square and t fails to be within this accuracy, 2 into 10 power minus 4, then you know that the program that computes the square root is not doing a good job. So it must be fixed. So this is a useful way for testing certain kinds of functions. So this was an overview of functional testing that I wanted to give you. In the next 3 lectures of this week, we are going to exclusively focus on input domain partitioning, equivalence class partitioning, because that is the most useful functional testing technique, and look at it in detail through examples and what would be various kinds of coverage criteria that we will consider for that. I'll stop here for now. Thank you.